Thanks everybody. I'm Corey. I'm a software engineer at Databricks, and today I'll be talking about what's new in MLflow. To start off, I'll provide a recap of some of the recent platform developments as well as the overall platform structure. Then we'll do some feature deep dives, taking a closer look at autologging integrations for scikit-learn, the new introduction of model input and output schemas, as well as input examples in MLflow Models, as well as MLflow's expanding plugin ecosystem. Finally, you'll learn about upcoming developments in MLflow and in Databricks more broadly. So to start off with a recap of the structure of the MLflow platform, the platform currently consists of 4 components designed to standardize the end-to-end machine learning lifecycle. MLflow Tracking is a centralized repository for all of the model training sessions across your organization, cataloging critical information, including hyperparameters, performance metrics, artifacts, and more. MLflow Projects is a tool for reproducible execution, ensuring that your machine learning code produces consistent results across platforms. MLflow Models is a standardized packaging format for your machine learning models, complete with deployment utilities for real-time and batch inference. And finally, the newest component of MLflow, the model registry, is a collaborative hub for model development, enabling you to version your models and transition them through the complete lifecycle from development through production and beyond. So now that I've provided that brief recap, I'd like to take a look at some of the latest developments in the MLflow platform. In MLflow Tracking, we've recently introduced support for scikit-learn autologging, as well as fast AI autologging. These dramatically simplify the process of instrumenting your machine learning code in MLflow Tracking. From a UI standpoint, we've made some significant UI accessibility enhancements, as well as artifact viewer improvements, including rich syntax highlighting and support for PDF rendering. Taking a look at MLflow projects, we now provide support for third-party backend plugins that we'll be talking about later, including a yarn execution backend. Additionally, we've expanded the set of artifact resolution capabilities for project parameters, enabling you to directly pass in data or model sources stored on Google Cloud Storage, Azure Blob Storage, FTP and SFTP servers, and many more. Taking a look at MLflow Models, as we'll discuss shortly, we've integrated support for model input-output schemas, as well as input examples. Additionally, we've introduced the capability for developers to plug in third-party deployment targets, as we saw in the previous talk about Redis AI. From a flavor standpoint, we've integrated native support for the Spacey model flavor. This enriches the NLP experience in MLflow. And finally, we can take a look at the MLflow model registry improvements. You can now set tags on your model versions and registered models. We've also enhanced the comparison view for model versions, enabling you to compare the schema across 2 prospective versions or more before making a decision about which model to move into staging or production. And finally, we've simplified the model archiving experience. You can now opt to archive all existing production versions of a model when you transition a new version into production. This simplifies and de-risks the upgrade process. What's really exciting about a lot of these new developments is that more than half of them have been contributed exclusively by third-party developers. So now that I've provided that overview of new developments, let's do a deeper dive into some of these standout features, including autologging for scikit-learn. So to start off with some motivation for scikit-learn autologging and autologging in general, we observe that instrumenting machine learning code in general is often very verbose and can become difficult to manage. In this example, we're going to walk through an instrumentation workflow using lower-level MLflow APIs for some scikit-learn training code. In this instance, we have an elastic net regression model with 2 parameters, alpha and an L1 ratio. We fit the model on some data, and once the model has been trained, produce some evaluation metrics. So if we were to instrument this code, we might begin by starting a new training session with start run. We could log our parameters, alpha and L1 ratio, using log param, and then proceed to train our model. Once we've produced a model and some metrics, we will log them using the MLflow log metric invocation. Additionally, we can leverage MLflow scikit-learn log model to persist that model, and finally wrap up our run using end run. What we quickly notice here, though, is that we've just written more instrumentation code than ML training code. And this is especially becoming the case as frameworks simplify their APIs. And we also note that ElasticNet is one of more than 100 models in the scikit-learn ecosystem that developers are constantly iterating on to achieve optimal results. As a result, because each of these models is parameterized by many variables and hyperparameters, there ends up being a lot of instrumentation code to maintain and upgrade as libraries evolve. Which leads us to a more unified API that users can seamlessly leverage to automatically record all of this information. With mlflow.scikit-learn.autolog, we automatically extract all of those relevant model hyperparameters, metrics, artifacts, and more. And we can take a look at this in the following example. So in this notebook environment, we have an initial data cell that loads in some training data from a housing data set, mapping attributes of a home to its sale price. The subsequent cell then instantiates that ElasticNet model that we saw a couple slides ago and performs training on this data. What we're going to go ahead and do is insert a new cell and very effectively instrument this training code by simply adding the mlflow.scikit-learn.autolog line. Once that's added, we'll then go ahead and execute our notebook cells. This will automatically capture all of the relevant information about our ElasticNet training. If we hop into the MLflow UI, we now see we have a new MLflow run corresponding to this training session. And we can go ahead and click in to explore the set of information that was logged. Right off the bat, we see that we have a collection of all of the important model hyperparameters, including those user-specified alpha values and L1 ratio, as well as other important variables, such as whether or not the data was normalized and the number of training iterations that occurred. Continuing downward, we can also take a look at the set of metrics. We see that scikit-learn autologging automatically computes relevant training metrics, including mean squared error and an R-squared value. Continuing downward to the tags section, we also see that autologging takes note of the model type and the specific model class that was trained. This enables you, for example, to search for all of the ElasticNet training sessions across your entire organization. And finally, let's take a look at artifacts. Scrolling down, we see that scikit-learn autologging has captured the model that we trained in MLflow model format with two flavors. One, the scikit-learn flavor, enabling you to load this model as a native ElasticNet object and evaluate it. And the other, Python function flavor, enabling inference at a higher level of abstraction as a Python function. Now, this workflow demonstrates just how easy it is to leverage autologging for instrumenting one-off model training. But we also recognize that hyperparameter optimization is an extremely important use case in machine learning in general and in scikit-learn. In fact, scikit-learn provides grid search CV and randomized search CV APIs for this purpose, and autologging integrates with those as well. So in this slightly modified example notebook, instead of fitting a single ElasticNet model with pre-specified hyperparameters, we've instantiated a grid search CV object to sweep over 10 potential candidate alpha values ranging from 0.1 to 1.0. As we did before, we're going to go ahead and drop in that autologging call. And after that, we'll execute these cells. What we expect to see happen here is that MLflow scikit-learn autologging will capture each hyperparameter sweep as a separate child run and provide insight into the performance of each candidate parameter. Hopping into our UI, we see we have a single parent run with a collection of children, each enumerating that relationship between the alpha parameter and an insightful performance metric. We can also select that parent run and click in to see that we've recorded some additional parameters. In this instance, we've captured the name of the estimator that we're fitting. So recognizing that we are training ElasticNet models as part of our hyperparameter sweep. We also capture the complete parameter grid, as well as the optimal value of that alpha parameter. Scrolling down, we can also take a look at the set of metrics and see that in addition to the training level metrics produced in the one-off model case, we've also retained the best cross-validation score corresponding to that optimal alpha value. Scrolling down to artifacts, we'll also take a look at the logged content there. In this instance, in addition to logging the grid search CV model itself, we've persisted the optimal elastic net model so that it can be easily reloaded and used for further training or for inference. Now that concludes the demo portion of scikit-learn autologging, and I'd like to call out that scikit-learn is just one of many autologging integrations already available in MLflow, including support for TensorFlow, Keras, Spark, FastAI, LightGBM, XGBoost, and Gluon, with most of these integrations being contributed by the community. And we're looking to rapidly expand the set of autologging integrations in the near future. Now let's talk about model schemas and input examples in the context of MLflow models. Historically, MLflow has always provided log model APIs, enabling you to save models from a variety of ML frameworks in a standardized format. And this format contains a lot of rich critical information, including a conda environment snapshot of the software dependencies used for training that model, the raw files and model graphs necessary to reload and perform inference or further training on the model, and a configuration file enabling you to interface with the model at varying levels of abstraction across languages. As of MLflow 1.9, we now incorporate input and output schema information into this MLflow model format, providing a direct view into the set of expected input columns and the set of produced outputs. This information is also carried forward from the MLflow model format into the MLflow model registry, enabling you to compare across model versions for schema differences as you debate whether or not to make staging or production level changes. This user interface enables you to detect potential incompatibilities before your models reach production. Let's take a look at the high-level workflow for associating a model schema with your MLflow model. In this example, we're going to leverage MLflow's infer signature API to extract a schema from our housing data set that we used in the previous example. Together, an input schema and an output schema combine to make a signature. And when we call this infer signature method on some example data from that data set, we obtain a collection of input and output columns. These are mappings from column names to data types. We see we have the year a home was built and the year it was sold, the square footage, zip code, and a more subjective measurement of quality. In terms of outputs, we have the sale price, as expected, with data type double. Once you've obtained a signature from your training or sample data, you can then seamlessly associate it with your MLflow model by passing that signature into the log model API calls that you're already making. And we can take a look at this example workflow in the context of schema validation. So once your MLflow model is associated with a particular input and output schema, it will then validate incoming data against that schema. In this instance, we can imagine swapping out that quality field with another field that's present in the same data set and has a very similar value range called condition. This is a very plausible mistake that one might make when evaluating a model of this nature. So if we were to take this invalid data input and pass it to our model, MLflow will automatically validate the schema of the incoming data and raise an informative mismatch error that prevents us from obtaining confusing or misleading results. And we can take a look at that in a real-time API context. In this notebook, the first thing that we're going to do is reload the model that we trained in the previous segment of the demo. Scikit-learn autologging already seamlessly captures the signature information, so the model that we produced in that segment of the demo already contains the signature. We'll go ahead and run this first cell, and right off the bat, we see that all of those expected inputs and outputs have been captured. The next thing that we'll do is load the model as a generic Python function for inference, and then construct that slightly modified or invalid example from the previous slide. In this instance, passing condition instead of quality as a data column. When we attempt to evaluate the model against this input, we see an extremely informative and clear error message indicating that the expected quality column is missing, and it's likely that the condition column replaced it. Now, it's worth noting that this schema validation is not limited to interactive contexts. Schemas are validated during batch scoring workflows as well as real-time inference. This ensures that the type safety, column ordering, and name validation is consistently applied across all of the environments where you're performing inference on your model. Now, we can return to that input and correct the mistake that we had made. We'll go ahead and substitute condition for the correct quality field. And after we've done that, we can go ahead and reevaluate our model. Going forward with that workflow, we see that our model correctly computes the inputs and produces a reasonable output. Let's also take a look at the integration of model schema information into the model registry UI. In this example, we've taken that model from the first segment of the demo and registered it with the model registry. Scrolling down in the model version UI, we see that it's captured this information about the model schema, and that information is displayed in a very accessible tabular format. We can also make comparisons between model versions and their schemas. From the model registry UI, simply select the group of versions to compare and press compare. This loads a sophisticated comparison interface, part of which compares the schema. Here we see the collection of input and output schema columns displayed side by side. In this instance, we have a column ordering sensitive comparison. So in this case, the second model version, which was trained on a slightly different data set, is shown to use that condition column instead of a quality column, as well as swap the zip code and year built fields. For many models, their inference procedures are column order sensitive, so this kind of information is extremely important. For users only looking to view the difference between two sets of schemas, that view can be collapsed further. And for users that don't care as much about the column ordering sensitivity, that can be toggled off as well, clearly highlighting the discrepancy between fields that are present in one schema and absent in another. Now that we've taken a look at autologging for scikit-learn and model schemas and input examples in MLflow models, let's talk about the expanding plugin ecosystem in MLflow. MLflow plugins enable you to seamlessly integrate your third-party code and infrastructure with MLflow. Third-party plugin code consists of one or more implementations of standard plugin interfaces provided by the MLflow project. Developers can write, test, and host this plugin code entirely independently of the core MLflow codebase. The MLflow library itself then uses Python entry point functionality to discover these third-party plugins at import time. When your plugin code is installed on a system, it registers these entry points, and when MLflow is imported, it discovers them, enabling users to interface with this plugin code using the same set of familiar APIs in tracking, projects, models, and the model registry. In terms of supported interfaces, the plugin ecosystem is fairly broad. We provide support for tracking storage and search plugins through the tracking store interface, tracking metadata collection plugins via the run context provider, plugins for model registry storage and search through the model registry store, project execution plugins through the project backend abstraction, and plugins for model deployment using the new deployment client interface. And creating a plugin is a straightforward process. Simply implement the plugin interface, or potentially multiple interfaces depending on your use case, by referencing the sample implementations provided on mlflow.org. Then add the corresponding entry points and upload your package to PyPy. Finally, MLflow maintains a collection of all of the community plugins on mlflow.org. You can contribute to that very easily. Now we'd like to talk about the new deployments API that was discussed in the previous talk. The deployments API is a pluggable way to create and manage new deployment endpoints in MLflow. It's already in use with the Redis AI endpoint and can be installed from PyPy, and our other existing integrations for deployments in MLflow are being ported, including Amazon SageMaker deployment and deployment to Microsoft Azure ML. On the right-hand side of the slide, we see that users can interact with these third-party plugins using the familiar MLflow deployments create CLI, simply specifying the deployment plugin backend's name using the -t flag. Similarly, project backend plugins are also a new addition, providing a pluggable way to execute MLflow projects on an expanded set of compute resources. This is in use for Yarn, and we're currently porting project execution on Kubernetes and Databricks. On the right-hand side, again, we see that the familiar MLflow run CLI can be leveraged against the Yarn backend simply by specifying the backend flag. To provide an overview of all of the currently provided community plugins, we see that MLflow includes an Elasticsearch backend for MLflow Tracking, model deployment to Redis AI, and project execution on Yarn that we just talked about, as well as plugins for artifact storage in SQL Server and Alibaba Cloud OSS. We're looking to rapidly expand the set of available community plugins and are very excited about seeing your contributions to the plugin ecosystem. Now that I've gone through those feature deep dives and given you a better sense of the new developments in MLflow, let's take a look at the exciting upcoming roadmap, both within MLflow and Databricks more broadly. First and foremost, I'm excited to announce that MLflow is actively working on integrations for model understanding and explainability within MLflow Tracking and MLflow Models. We're really excited to share more details on this active development, and we'll be doing that at the Data and AI Summit, which we encourage you all to attend. We are also in the process of introducing support for tensor input and output schemas, extending the utility of this feature beyond columnar data. And finally, we are working to expand the set of autologging utilities that automatically include input examples and schema collection. In this instance, very soon, you'll see that XGBoost, TensorFlow, and more model frameworks will automatically infer model signatures and provide the capability to collect input examples during the autologging and training process. I'd also like to call out that for MLflow users on Databricks, the turnkey model deployment and serving solution is also broadly available in public preview and is accessible on most of your workspaces. This provides a seamless mechanism for serving your MLflow models as RESTful endpoints. And for more information about MLflow updates and Databricks developments more broadly, I'd like to reiterate what Jules and Ryan called out, which is that the Data and AI Summit is coming up from November 17th through 19th. General admission is completely free, and you can register on our website at databricks.com/data-AI-summit. As always, you can get started with MLflow by installing the library on pip. Please make contributions to the code base and raise issues on github.com/MLflow, and visit our website at mlflow.org for documentation. We also maintain a Slack server. I've linked it there, and we're looking forward to your feedback there as well. Thank you, and I look forward to answering your questions.
Well, thank you, Corey, for that introduction and a walk through some of the deep dives of the new features, as well as what's coming up that we are sharing with the community. There are a few questions that actually come up. I answered some of them, but actually, if you want to probably add something from your perspective, one question from Sri Chandana is, how can you use MLflow in model governance?
Specifically related to Git, it looks like.
Well, I mean, if I wanted to use model governance, how would I use MLflow? And my answer to the question was that we provide, at least in some parts of the model MLflow managed registry, the set of actors that give you the governance of who can do what at what time and when. We provide the lineage of all the models evolution from the point that you train, how the transition was made. And then what you showed about the model validation of inference actually gives you the ability to say, well, if your model has changed, we actually enforce that you make sure you send in the right amount of input so you get the right output and schema validation. So those were the highlights. Was there anything else that you actually might want to add to it?
I think you did a great job of covering that. So the lineage information, it's important to note, is really rich and is propagated from training time all the way through the model registry. There's a link back to that source run, and the addition of schema information, as Jules mentioned, provides additional validation to check against potential degradations for production application deployments. I think you said it really well. Thanks so much.
Right. And as you pointed out earlier, the new features which are coming up, which is model explainability, and that aspect also fits in well with the governance, because you won't be able to justify, how do your model predict the way it is? And so that aspect of explainability also contributes and adds to the whole functionality of model governance.
Absolutely.
Okay, let me see any questions there. Is there any Git resources related to MLflow that can be used in governance?
Yeah, so we have plenty of examples of the end-to-end model training lifecycle, which leverage both MLflow Tracking and the model registry and that model format that contains the schema. That's all hosted in our GitHub repository and the examples subdirectory. You can also check out additional resources, example workflows on mlflow.org. And if you're leveraging MLflow on Databricks, we have additional examples there. So there's a lot of awesome material.
Right, and just to add to what Corey said, is that we're also working on with our field engineering, with our SMEs, to create what we call the best practices guide, which will cover aspects of model governance in there as we have more and more functionality coming. And that will be sort of a working document, a living document that's going to evolve over time. And we can share that not only with the MLflow community, but also with our customers as well.